Okay, good. So first of all, I just want to thank you, Colin, Avishai, and Joel for another year here in this very wonderful workshop. And also, I was not brave enough on Monday to say some words about my relation with the Santa Cruz people, and I would like to take a minute to explain a bit my story also. I came here 10 years ago, same as Mark, just arriving at the beginning of August 10 years ago. And I was going after the PhD to meet very big names in astronomy, like Joel, Avishai, Sandy, and I was super nervous when I arrived here. And my memories are that I found people in a very friendly environment with very, very brave discussions, but still giving a lot of credit to the students and allowing the students to participate in any of the discussions. Although, like myself, I was a completely outsider on the field, no, because I was doing galactic dynamics. So I remember in a very nice way these times, and I am the person that I am the scientist I am because of being here in Santa Cruz the last 10 years. So I just wanted to say that, and thank especially Avishai, that I think that we all miss him a lot here this year, so hopefully we will meet him again very soon. Good, so said that, let me start with my presentation. I will not talk about budget or space missions. Maybe next year I can come to talk about a space mission. But this year I am going back to what was my work when I was doing the PhD, and that I took again back with a student that presented the PhD last year and now is a postdoc with us in Lund, that is working in the galactic dynamics of Milky Way-like galaxies. But first of all, because I know that most of the people here probably is not a lot onto the dynamics or the details on these non-axisymmetric structures, just a very few words, very broadly speaking. There is a lot of text. I will not go all over it. But just to say, first of all, for bars, I will go to spirals later. Bars are basically the main global perturbation that you can have in this collisionless gravitational fluid. It's very easy to form bars in this kind of situations, but it's also easy to destroy them if you end up having a central concentration, or even if you don't have a sink of angular momentum to really convert circular orbits to bar-like orbits. I will go to the orbits later. And also, they are kind of difficult to simulate in simulations that doesn't have a high resolution enough. Why is that? Well, if we go to the different kinds of bars, first of all, we have a first kind of bars that is the ones that generate first and very fast, that are the ones that are basically made by which are called the X-shaped orbits. Are very simple orbits, are orbits basically that in general, the simplest ones are just elliptical orbits that are the skeleton of the bar, and then these ones, through resonances, can grow through other kinds of orbits, a bit more complex, that are also a bit more difficult to generate in low-resolution simulations. For example, you can have these very clear loops here, that if your simulation, for example, is not high-resolution enough, you are not going to capture. You are going to end up in a bar that is very simple, just generated by these elliptical orbits. Things get a bit more complex with the second mode of perturbation, that is the vertical one, and it happens when it's in a thing that is called the buckling, and suddenly you have orbits in the vertical direction that looks like that. And basically these ones are the ones that build what is called the X-shaped P-naught bar. These are also very difficult to generate in simulations if you are not careful with the resolution that you have. And also, well, probably in observations you can have some biases if you don't take into account that bars, these bars, for example, can be easily observed if you are edge-on, but these ones cannot be observed because it doesn't have a very good vertical structure. Apart from the orbital structure in observations, well, in observations we see many boxy P-naught bars. No? You can see this very beautiful X-shaped structure here. This is basically showing the orbits, these vertical orbits after the buckling. And the question that I put here to the observers, especially the ones that observe now bars in the high redshift, and Mark was talking about that yesterday, is that these bars that they observe, if they have also 3D structure. So are these bars at high redshift bars that went through the buckling process, or is something that generated so fast or in the disks that are not kinematically cold enough to allow this kind of orbits? I am not sure. I have not seen any paper about the 3D structure of high redshift bars. Maybe somebody is working on that. I would be happy to talk about that with somebody. And also, a word of caution, there are lots of works of people analyzing bars in simulations. It's good to do it. I think it's very interesting, but also we have to be very cautious that these bars in simulations, if your resolution is not of tens of parsecs, you are not capturing these orbits that are the ones of the X shape, for example, or even the more complex orbits in the X family. So important to take into account that we generate bars in simulations, but maybe the bars in the simulations are not the bars that we observe in real galaxies. Okay, all this being very complex because in observations we only have a single snapshot and we don't have information of the specifics of the orbits of the bars in these external galaxies. But thanks to the Gaia revolution, now, for the first time, we can do an analysis with individual stars of a bar disk galaxy. And this is the work that we have been doing with the people in Barcelona, that is analyzing the LMC disk galaxy. That is our companion, this satellite galaxy of the Milky Way, that after getting all the Gaia data in the DR3, for the first time, we could get completely detailed kinematic maps, both for the radial velocity and for the tangential velocities, and we saw for the first time the quadrupole of the bar of the LMC. And also we have the information of the individual galaxies, sorry, for the individual stars, so we can kind of start doing some orbital analysis. But we also don't have detailed simulations of what happens with the LMC, and LMC is interacting with SMC and the Milky Way. So what we decided was to do a very big suite of simulations, also with the corresponding resolution tests of the interaction of these systems. And this is the Kratos set of simulations that we published last year with Oscar. And you can see different morphologies with different kinds of bars. And also, if you see in the vertical structure here, in some of the cases we have the buckling of the bar. So we will be using these simulations to test many of both the observations that we are having and also the strategies that the observers do to compute the properties of the galactic bars, to test if these mechanisms really do work with the fully information of a galaxy. The first thing that we wanted to test is something that has been we use it a lot for external galaxies to really constrain the properties of the bars. That is the Tremaine-Weimer method. Is used to compute the pattern speed of the bars and basically takes advantage of thinking that the galaxy is in, you can think that the tracer in the galaxy obeys the continuity equations. That is a system that is very stable, and also that you can somehow cancel out the effects of the rotation of the galaxy, basically using some slits in the direction that crosses all the disk in the galaxy, crossing also the bar. No? So basically you take one slit and you integrate all the information, kinematic information and density information in each one of the slits, and through this equation that you can get from the continuity equation, you can end up with a linear relation in where you can get the pattern speed of the bar. This is applicable if the system is completely stable and obeys the continuity equation. With the LMC, the next step we could do is that we can extract this effect of the inclination of the disk, and we can really completely project the LMC to the being completely phase-on. And then the equation gets a lot more simple. And we did it, and we computed a pattern speed for the LMC bar that is of 30.4. Is this value the true value? Well, now we can test it because we have all the information for the LMC. But we wanted also to use other methods for the pattern speed. Another one is the B-symmetric method, was used to compute the pattern speed of the bar of the Milky Way. And basically this one is only available if you think that the rotation curve of the Milky Way is very stable and that the potential is very, very soft. And then basically what you do is you take a Fourier mode of the galactic bar, and in the place in where the angle of the main Fourier mode drops, you think that there is the corrotation there, you place the corrotation, and having the rotation curve and the corrotation, you get a pattern speed. In this case, for the LMC, we got 18. So we have 18 and we have 30. Two different methods, two different answers. But we went a bit further, and we used a very recent method, the Denen method, that till now was being used only for simulations, and you can get the pattern speed of the bar or the spirals in a simulation using a single snapshot. It's the same strategy as the Tremaine-Weimer, but now having information of the individual stars. And with this, you get absolutely the true value. And it has been tested in many simulations that basically using both finite differences that give you the true value because you see exactly the rotation of the structure, you get exactly the same value if you use the Denen method. And now we can use the Denen method with the LMC because we have the information of individual stars. And which is the result of this very robust method? We got -1 kilometers per second per kiloparsec. So it looks like using the Denen method, the bar of the LMC is stopped, doesn't rotate. It was very strange. I will go to that later. we know that the Tremaine-Weinberg maybe is not working. We already know that in some occasions it's not working. For example, when the system has multiple patterns, like a bar and spiral arms and different non-axisymmetric structures. But we wanted to test it very well, how the Tremaine-Weinberg can be used and in which situations can be used. We used many simulations, but also we took advantage of having the LMC, that we can basically take it, make it face on, but also inclinate it and rotate it, so we have the bar direction in different directions with respect to the line of sight. And we tested here in this plot I show as function and how the bar is orientated towards us, the pattern speed that we recover. You know, the NN method gave us almost 0. The bisymmetric method gave us 20. The traditional Tremaine-Weinberg gave us 30. And basically, when we rotate the galactic bar with respect to the line of sight, we can see that using Tremaine-Weinberg method, we get absolutely crazily different values. So really, you cannot trust in most of the occasions in the Tremaine-Weinberg in a system like the LMC that is quite perturbed, the bar is a bit miscentered, and also you have some spiral arms. But this is the situation of most of the galaxies in the universe. All of them, most of them are perturbed. So it's very dangerous to use blindly the Tremaine-Weinberg method. What we want to do as a next step is to make a very detailed computation of the errors that you are doing depending on how the bar is oriented to respect to us. And this is something that we are basically working with Oscar for a next paper. And, I'm sorry because I also wanted to give you another warning here that it's important that if you do the tests of the Tremaine-Weinberg in simulations, that you are sure that in these simulations the bar has all the orbits that the bar has. Because if the bar only has the X elliptical orbits, your Tremaine-Weinberg method will work, because basically it's very easy to cancel out the other parts of the rotation of the galaxy. Just this warning, because there are some works doing that, and we want to test go a bit further on the testing of the Tremaine-Weinberg. This was one of the first results. The second result, and very fast, is why the LMC looks like is a galaxy with a stopped galactic bar. And we went through all the Kratos models and also to some of the literature, and we saw that basically a tidal interaction like the one of the SMC towards the LMC basically can stop completely the galactic bar for some mega years. And you can see it here. This is one example. You see now that the bar is completely stopped and then reinitiates again the rotation after this moment of being stopped by the tidal interaction. So we got a letter accepted with Oscar this year in where we explain very well how you can stop a bar by tidal interactions. Okay, and going very fast to the very last part of my talk, I have like 2 minutes. I have 7 minutes. I am talking always too fast. Anyway, second part, spiral arms. So this was my main topic of research during my PhD thesis. I was in the Gaia team in Barcelona doing a lot of pre-analysis before launching the Gaia satellite. And in that times, we had this picture about the Milky Way with a very nice galactic bar and very nice 2 bisymmetric main arms. And suddenly now, after all the analysis that we have from the DR3, we know that the Milky Way is probably more similar to that, with a very nice defined galactic bar, an inner ring, and lots of spurious arms, but not a clear dominating bisymmetric spiral structure. Something that tells us how uncertain is everything related with the spiral arms, even with own spiral galaxy. Related with the theories, there are many theories trying to explain the spiral structures. We know that the spiral arms have different natures. In a single galaxy, you can have very different kinds of spiral arms. The bisymmetric, strong spiral arms usually are not the same as the spurious spirals. And there are many theories that try to explain that. The pure density wave, the traditional one that you may probably all know from the lectures you got in the astronomy courses, that is the linear issue density wave. With a very beautiful extension, I really recommend that if you like galactic dynamics, you go through it. Sharon Mate published last year a nice extension of the linear issue development for the spiral structures that now includes the spirals that are with a much larger pitch angle. So now you can explain most of the spiral arms using this theory. A second theory that was developed in the early 2000s and somehow abandoned, but is the one from my school and is the one I will be talking about. That is the material density waves. These are the spiral arms that also contain stars that are moving through the spiral arm, but at the same time they are density waves that are going through this with a rigid pattern. I will talk a bit more about the invariant manifolds later. And then you have other spurious spirals that can be explained basically by winding of local material density perturbations, and also star-forming spirals that are very short-lived. And also, I will go to this kind of spiral structures because for a long time we have seen that there is an obvious connection between spirals and bars. It looks obvious from the images, but nobody has been really working on trying to understand why this connection is happening. No? And this is basically well explained by the material density waves, the invariant manifolds. Shorts, invariant manifolds is a very beautiful theory and simple that tells us that spiral arms and rings can be formed just because when you have a non-axisymmetric structure in the center of the galaxy, you suddenly generate Lagrangian points, and from the Lagrangian points, you can get orbits in where the particles, the stars in this case, can be trapped, and follow them. And then you can generate all this variety of structures, just changing the pattern speed and the strength of the galactic bar. Okay, so it's very simple. It should happen because these orbits, of course, exist in nature when you have a non-axisymmetric structure. The question is how abundant these are, and if these are the ones that dominate the spiral structures when you have a bar. We wanted to test that. It has never been tested. It was challenging because it involves many steps with many different strategies to follow. But now, after many people producing new codes to analyze the simulations, we are in a time that we can test the invariant manifold theories in simulations. And this is what we are doing with a student in Barcelona. Basically, this is the process that we do. We take the simulation, we compute the Lagrangian points, we compute the Lyapunov orbits, the energies, and then we take all the particles of the simulations and we try to see if these are captured or not by the invariant manifolds. And the preliminary results we have, hopefully maybe next year I can come with a paper already submitted. We are seeing that indeed, when you take a simulation, isolated this simulation that generates a bar and the bar generates a spiral arm, up to, in some cases, 60% of the stars in the spiral arm region belong to orbits that have the energies to be tied to the invariant manifolds. So what we are seeing, and when we analyze also it in time, here in this diagram is basically the m=2 mode of the spiral structure. So as higher, it means that the spiral arm is higher. You see here a spiral arm that is a transient. And here you have the fraction of captured stars as function of time in parallel with the amplitude of the Fourier mode. So you can see a very clear correspondence between the number of captured particles and the amplitude of the spiral arm. And what we are seeing is basically that the invariant manifolds put in place the skeleton of the spiral arms, so the density wave can be generated initially by the invariant manifolds, and then it gets self-gravitant, and other particles can be trapped by the density wave. Then this could be, is not that all the particles in the spiral arms belong to the invariant manifolds, but yes, the invariant manifolds puts in place the density wave that then starts rolling around the galaxy. And okay, and I think that's all. Probably I am almost out of time. This is my summary about many amazing, interesting things in galactic dynamics that probably cannot be applied yet to high redshift, but who knows if soon we will be able to say something about that. So the outcomes, trivial invariant method needs to be studied further. With higher resolution simulations and giving the details on the errors that we are making when we use trivial invariant for different configurations of the bar structures and also with different non-axisymmetric structures in disk, that the tidal interactions can stop bars. So these very slow rotating bars that we have been observing in the universe maybe are due to some previous interaction with the satellite, and that the invariant manifolds can really be the skeleton of the spiral structures in varied galaxies. We will continue this work with Oscar Aguers, Josh Blenhawthorne in Australia on adding hydrodynamics on all these things that I have been explaining. And that's all. Thank you.
Questions?
Hey, thanks. I'd like to suggest caution about attributing spiral arms to bars.
Mm-hmm.
I think that's something that is observationally accessible in the sense of you can measure the pattern speeds of both of them, but obviously some galaxies have spiral arms and not a bar, and when we see a bar and a spiral arms together, it is not established that the bar in fact drives the spiral arms, and there's some very old work so that you can have different pattern speeds and it can look like the bar is attached to the spiral arms, but it isn't necessarily.
I 100% agree. So as I said at the beginning when talking about the different theories, galaxies contain very different spiral structures, and in some of them, the manifolds can be dominating. In some of them can be, for example, a tidal interaction with a companion that also drive a bisymmetric structure. So I totally agree. So another thing is to find out how many of them can contain invariant manifold. Yeah.
Okay. If there are no more questions, we can give an applause to Santi.